students. In my last class, I completed second chapter, electrostatic potential and capacitance. Today, I'll start third chapter, that is current electricity. So before going to define what is electric current, we shall discuss some basic things. Okay? Suppose if I consider a point charge which is at rest, it produces electric field the region all around the charge. So it produces electric field. Also called as electrostatic field, which we learned in the first chapter itself. Okay. Suppose the same charge kept in uniform electric field. You just imagine this line represents uniform electric field. So I place a charge in the uniform electric field. Either it may be positive charge or negative charge. So when the charge kept in uniform electric field, this charge experience force. What is the magnitude of the force? F is equal to Q into E. Even this equation also we learned in the first chapter itself. So one more thing, suppose if we set a charge to move in uniform magnetic field with a velocity v. So like this. Look at this. This is magnetic field. The charge is moving with a velocity v, makes an angle theta. So what will happen? It experiences a force. The magnitude of force is F is equal to BQV sin theta. BQV sin theta. So here charge is at rest. It producing electrostatic field, the space or region around it. The same charge when kept in uniform electric field, it experiences a force. What is the magnitude of force? F is equal to Q into E. Suppose if we set the charge to move in a magnetic field with a velocity v, making an angle theta, again the charge experiences a force. Then what is the magnitude of the force? BQV sin theta. So for this we have one small expression you are going to understand in the further classes. When the charge is at rest, it produces electric field. Suppose if the charge is moving, when the charge start moving, what it produce? It produce magnetic field. It produce magnetic field. So these are the general things which we come across in the first chapter. Now I'll consider one metallic conductor, iron rod or a copper rod. Okay. Consider as a metallic conductor. We know that metallic conductor possesses plenty of free electrons, and also atoms in the metallic conductor are closely packed like this. So they are closely packed. So this is nucleus, nucleus, nucleus. So it possesses many number of free electrons. They are loosely bound with the nucleus. They are loosely bound with the nucleus. So these electrons are called as free electron. Free electron. Free electrons. Also called as valence electron. How do they become free? Due to room temperature, they will get some energy. Due to room temperature. They acquire some amount of energy. When they acquire some amount of energy, suppose this is outermost orbit of this atom. This is the outermost orbit of this atom. This is the outermost orbit of this atom. When they acquire some amount of energy because of room temperature, the outermost electron start jumping from outermost orbit of one atom to the another atom, like this, like this. They are moving in random motion, not in a particular direction. I'll write one more diagram. Metallic conductor. So they start moving like this in an irregular manner. Not in particular direction. So in this way they are moving in random motion. Suppose if we make this electron to move in a particular direction, what we will get? We will get electric current. Or if we set this electron to move in a particular direction, they constitute current or nothing but electric current. The meaning of current is nothing but flow. Then what is electric current? It's a flow of electric charges. It is the flow of electric charges. How can we set this electron to move in a particular direction? I have to set electric field. So to this metallic conductor, two ends are there, no? Across the two ends of the metallic conductor, I'll connect a battery or a cell, any source of current. What are the source of current? Either it may be battery, or it may be cell, or it may be generator, or it may be dynamo. So here I consider a battery. So battery is connected across the two ends of the conductor, in which the electrons are moving in irregular manner. They are moving in random motion. One thing you have to make a note: if the charges are moving in a random motion in the metallic conductor, they do not constitute any electric current. Okay, so here electric field is applied. When the electric field is applied, what will happen? Electric field is set up in the metallic conductor. In the metallic conductor. So this is in the absence of electric field, which means not yet connected. You just imagine, not yet connected. So they are moving in random motion. Electric field won't be there. Initially electric field won't be there. They are moving in random motion. If we connect, what will happen? If we connect across the two ends of the metallic conductor, what will happen? Let's see now. See. So current is flowing from positive terminal of the battery to the negative terminal of the battery, and the electric field set up in this direction. So electron experience a force or this electric field exerts a force on electron, they start moving in particular direction. Look at the diagram. Look at the diagram. See, they are moving in irregular order, in random motion, when there is no electric field is applied across the metallic conductor. Soon after connecting a battery across the two ends of the metallic conductor, electric field set up in the metallic conductor, and the electrons are start moving in one particular direction, then they constitute electric current. So we can define electric current as electric current can be defined as rate of flow of electric charges. See, electric current can be defined as rate of flow of electric charges. Mathematically, I can write the equation I is equal to Q divided by T. So this is a mathematical expression for electric current. How can we measure a strength of electric current in the metallic conductor? By using SI unit, ampere. So ampere is the SI unit to measure strength of electric current in the metallic conductor. And even the charges may flow through the metallic conductor, through the electrolytic substances, even in the gases. So this is very basic information regarding electric current. So look at charges at rest producing electric field. When the charge kept in uniform electric field, it experiences a force F is equal to Q into E. If we set the charge to move in the magnetic field with a velocity V, it experiences a force that is B QV sin theta. When the charges start moving, they produce a magnetic field. And look at here, in case of metallic conductor, due to the thermal excitation or due to the room temperature, electron may jump from one atom to the neighboring atom. They start moving in random motion. When they are moving in irregular motion, that is a random motion, they do not constitute any electric current. If the same charges set into a particular direction like this, they constitute electric current. So we can state like this: electric current can be defined as rate of flow of electric charges. Now we'll see types of current. First one, steady current. First I'll explain what is steady current, then I'll give the definition. Now I'll consider a metallic wire. Just imagine this is a metallic wire or a conducting wire. A and B are the two ends. Okay? The charges are flowing through the wire from one end to the other end. Suppose in first second, the magnitude of the charge that flow through the wire or that flow through the conductor or that flow through the metallic conductor or metallic wire is, for example, 2 coulomb. In the next once again, the charge that flows through the conductor again 2 coulomb. The next once again If the charge that flow through the metallic conductor is 2 coulomb, then what is the current? I is equal to Q by T is the equation. In the first second, what is the magnitude of the charge? That is 2. So what is the current? 2 amps. In next 1 second, the current that flow through the metallic wire is 2. So what is the current? 2 amps. The next 1 second, what is the current that flows through the metallic wire? That is 2. So what is the current? 2A. Look at here. The magnitude of the current is same. The magnitude of the charge that flows through a conductor is same every second. Such current are called steady current. So I can write the statement like this. The magnitude of flow of charges through a conductor remains same or constant every second. Such current is called as steady current. I can represent graphically. See, along x-axis time and along y-axis current. Here once again, next 1 second, that is 2, 3, 4 and 5, 2 coulomb, 4 coulomb, 5 coulomb. 2 coulomb, 4 coulomb, 6 coulomb. For an example, I am giving the numerical values. In first once again, what is the magnitude of the charge that flow through the metallic wire? 2. Next once again 2. And next once again 2 only. So you will get the graph like this. So it is said to be steady current. Move to the next type, that is varying current. Varying current. Okay. So here also I'll consider a metallic wire or a conductor of end A and B. The same procedure I will follow. Suppose in first second, the magnitude of the charge that flows through the metallic wire is 2 coulomb. In next 1 second, 4 coulomb. Next 1 second, 6 coulomb. In next 1 second, again it may be 4 coulomb. It may increase or decrease, but one thing you can notice, keep on changing. Then what will be the current? I is equal to Q by T. In first once again, what is the magnitude of the charge? That is 2. So 2 amps. In next once again, what is the magnitude of the charge? 4. So 4 amps. In next once again, what is the magnitude of the charge that flows through the metallic wire? That is 6. 6 amps. So what is in the next 1 second, what is the magnitude of the charge? Again it decreases 4. So 4 amps. So keep on changing. So what is the statement? Can write the magnitude of flow of charges through a conductor changes. every second. Either in increasing order or in decreasing order. So every second the magnitude of the charge which flows through the metallic conductor changes. As the magnitude of the charge which flows through the conductor changes, then current also changes. So graphically I can show like this. Along x-axis time, along y-axis current. So increasing order like this or decreasing order like this. Graphical representation for varying current. Varying current means the magnitude of the current varies each second, or the magnitude of flow of charge through a conductor changes every second. Whereas in case of steady current, the magnitude of flow of charge through a conductor remains same every second. As the flow of charge through the metallic conductor remains same, current also same. So it is said to be steady current and it is said to be varying current. Now, third type, direct current, DC. Now, what I will do means, the two ends of metallic conductor, that is A and B, connected to a battery. This is positive terminal of the battery, negative terminal of the battery. So look at this. This is the direction of current from positive terminal of the battery to negative terminal of the battery. So in case of direct current also, in first second, the current that flow from positive terminal of the battery to the negative terminal of the battery, what is the magnitude? It may be 2 amps. In next 1 second, 2 amps. The next 1 second, 2 amps. And all the times the current is moving from or flowing from positive terminal of the battery to the negative terminal in a single direction. Positive terminal to the negative terminal. Such current is said to be direct current. So what is the statement? Magnitude and direction of current remains same or constant. See, both the magnitude is not changing, 2 amps, 2 amps, 2 amps. Even the direction of the current is always from positive terminal of the battery to negative terminal of the battery. Such current are said to be direct current, that is DC. Magnitude and direction of current remain same. Graphical representation for direct current. Two amps, 4 amps, 6 amps for an example. For 1 second, 2 amps. Next 1 second, 2 amps. Next 1 second, 2 amps only. In a single direction. You may notice the graphical representation regarding direct current is same as that of the graphical representation which we studied for steady current. But one difference is there. In steady current, we discussed only magnitude of flow of charges, not a direction. But here we are particular about the direction of current also. Look at the statement, magnitude and direction of current remain same in case of direct current. So this represents a graphical picture regarding direct current. Next one. Alternating current. AC. Okay, so here a metallic wire of end A and B is connected to an AC source. Look at the symbol. This symbol represents AC source, whereas this symbol represents DC source. DC, suppose if it is like this, AC. So here the metallic wire is connected across AC source. This end 1, end 2. Suppose the current which is flowing from end 1 to the end 2. Now initially it is flowing. The maximum current that flows from one end of the AC source to the another end of the AC source is, for example, 3 amps. Then how the current flows? Like this, initially started with 0, then 1 amps, then 2 amps, then 3 amps, then again 2 amps, then 1 amps, then again 0. From 1 to 2. One end of the AC source to the other end of the AC source. So it is started from 0, here 1 amp, 2 amp, started from here 0, 1 amp, 2 amp, 3 amp, again 2 amp, 1 amp, 0 during the first half of the cycle. In the next half of the cycle, the current start flowing from the second end of the AC source to the first end of the AC source. There also the same thing, 0, 1 amps, 2 amps, 3 amps, 2 amps, 1 amps, again 0, but the direction 2 to 1. Then what is the graphical representation? So like this. Yes. Started from 0, it reaches maximum. What is the maximum current? We consider 3 amps. Again it start decreasing, 2 amps, 1 amp, 0 during the first half of the cycle. During the second half of the cycle, means it changes the direction from end 2 to the end 1. The first one is end 1 to the end 2. During the second half of the cycle, again it's increasing, 1 amp, 2 amp, 3 amp, 2 amp, 1 amp, 0. So like this it alternate. So what is the statement? The magnitude of current changes periodically and direction changes alternatively. The magnitude of current changes periodically. Look at the value. And the direction changes alternatively in this way. Such current is said to be alternating current. Anyhow, in detail, you will learn more things regarding alternating current, because we have a separate chapter as alternating current in the second PUC. Okay, so these are the types of current. steady current, varying current, direct current and alternating current. Steady current, the magnitude of flow of charge through a conductor remains same every second. Varying current, the magnitude of flow of charge through a conductor changes every second. Direct current, the magnitude and direction of current remains same. Alternating current, the magnitude of current changes periodically and direction changes alternatively. So these are a very basic information regarding the chapter current electricity. So in my next class we will discuss more information regarding the chapter current electricity. Thank you.